Chapter 12. Radioactivity. F. Modern Physics. Syllabus. First, radioactivity and changes in the nucleus. Background radiation and safety precautions. Scope of syllabus. Brief introduction, qualitative only, of the nucleus, nuclear structure, atomic number Z, mass number A, radioactivity as spontaneous disintegration, alpha, beta, and gamma, their nature and properties, changes within the nucleus. One example each of alpha and beta decay with equations showing changes in Z and A. Uses of radioactivity, radioisotopes, harmful effects, safety precautions, background radiation. Radiation, X-rays, radioactive fallout from nuclear plants and other sources. Nuclear energy, working on safe disposal of waste, safety measures to be strictly reinforced. Second, nuclear fission and fusion, basic introduction and equations. Structure of the atom and nucleus. The discovery of electrons by Sir J.J. Thomson and the scattering experiments of alpha particles by Rutherford and others towards the end of the 19th century led to the following structure of an atom and its nucleus. Structure of an atom. An atom consists of electrons, protons, and neutrons. The protons and neutrons reside inside the nucleus of the atom, which is at its center, while the electrons revolve around the nucleus in some specific orbits in which they do not radiate out energy. Such orbits are called the stationary orbits or stationary shells. In each stationary shell, the electron has a definite structure of the atom and nucleus. The number of shells of an atom depends on the total number of electrons in it, so the number of shells is different in atoms of different elements. The maximum number of electrons in a shell can be 2n raised to 2, where n is the number of that shell. The various shells around the nucleus for n is equal to 1, 2, 3, 4, 5, 6, 7 are named as K, L, M, N, O, P, Q respectively, and these shells can accommodate at the most 2, 8, 18, 32, 50, 72, 98 electrons respectively. The electrons in different shells have different energy which increases with the increase in the number n of that shell. The size of an atom is determined by the radius of the shell of its outermost electron, and it is of the order of 10 raised to minus 10 meters. The electron has a negative charge equal to minus 1.6 into 10 raised to minus 19 coulomb, or minus E, and its mass, Me, is nearly 9.1 into 10 raised to minus 31 kg, which is approximately 1 by 1840 times the mass of nucleus. The nucleus is at the center of atom, whose size is of the order of 10 raised to minus 15 meter to 10 raised to minus 14 meter. That is 10 raised to minus 5 to 10 raised to minus 4 times the size of the atom. It consists of protons and neutrons. The proton has a positive charge equal to plus 1.6 into 10 raised to minus 19 coulomb, or plus E, and its mass, Mp, is nearly 1.67 into 10 raised to minus 27 kg. The total number of protons in the nucleus determines the place of the atom in the periodic table and is called the atomic number of the element of that atom. The atomic number of an element is denoted by the symbol Z. The neutron is an electrically neutral particle that its charge is equal to 0 and its mass Mn is also nearly 1.67 into 10 raised to minus 27 kg, which is equal to that of a proton. The protons and neutrons, which are the main constituents of the nucleus, are called the nucleons. The total number of nucleons in the nucleus is called the mass number of the element, and it is denoted by the symbol A. The nucleus is thus positively charged, and its total charge is plus Ze. The mass of nucleus is approximately 8 times the mass of a proton. The mass of an electron is negligible as compared to that of a proton or a neutron. Hence, total mass of an atom can be considered to be same as the mass of its nucleus. Thus, we can define the atomic number and mass numbers as follows. Atomic number. The atomic number of an atom is equal to the number of protons in its nucleus, which is same as the number of electrons in a neutral atom. That is, Z is equal to number of protons in the nucleus of an atom. Mass number. The mass number of an atom is equal to the total number of nucleons, that is, the given of the number of protons and the number of neutrons in its nucleus. That is, A is equal to number of protons plus number of neutrons in the nucleus of an atom. Symbol, charge, and mass of electron, proton, and neutron. Here's a table showing parameter, electron, proton, and neutron. Symbol of electron is E, proton, P, neutron, N. Charge of electron, minus 1.6 into 10 raised to minus 19 coulomb. Proton, plus 1.6 into 10 raised to minus 19 coulomb. Charge of neutron is 0. Mass of electron, 9.1 into 10 raised to minus 31 kg. Mass of proton, 1.67 into 10 raised to minus 27 kg. Mass of neutron, 1.67 into 10 raised to minus 27 kg. Model. An atom is electrically neutral, therefore the number of protons in the nucleus of an atom are equal to the number of electrons revolving around the nucleus of the atom. If Z is the atomic number and A is the mass number of an atom, then the atom contains number of electrons equal to Z, number of protons equal to Z, number of neutrons equal to A minus Z. The atom is specified by the symbol XAZ, where X is the chemical symbol for the element. The actual size of an atom is very small, nearly 10 raised to minus 10 meter, which is invisible. But just to understand the distribution of its constituents, we can draw the model of an atom not to the scale. Examples. 1. The lightest atom is hydrogen, whose mass number A is 1 and atomic number Z is also 1. It is represented as H11 and it has 1 proton in the nucleus and 1 electron in the K shell as shown in figure. Example 2. The helium atom has the mass number A is equal to 4 and the atomic number Z is equal to 2. It is represented as He42. It has 2 neutrons and 2 protons inside the nucleus and 2 electrons in the K shell. Example 3. The sodium atom has atomic number Z is equal to 11 and mass number A is equal to 23. It will have Z is equal to 11 protons and A minus Z is equal to 23 minus 11 is equal to 12 neutrons inside the nucleus, and Z is equal to 11 electrons distributed in the K, L, and M shells. 2 in the K shell, 8 in the L shell, and 1 in the M shell, as shown in figure. 1. If an atom undergoes a chemical change, there is a change in the number of orbital electrons of the atom, whereas if the atom undergoes a nuclear change, there is a change in the number of nucleons inside the nucleus of the atom. 2. A nuclear change requires much higher energy of the order of few mega electron volts, which is nearly 10 raised to 6 times as compared to the energy required for a chemical change, which is of the order of few electron volts only. 3. In a nuclear reaction, the atomic number or number of protons and the mass number or total number of protons and neutrons remain conserved. In other words, the total sum of atomic numbers of the reactants is equal to the sum of atomic numbers of the products. Similarly, the total sum of mass numbers of the reactants is equal to the sum of mass numbers of the products. Isotopes. The atoms of the same element having same atomic number Z but different mass number A are called isotopes. Obviously, the isotopes have the same place in the periodic table as it depends on the atomic number Z. The atoms of isotopes have the same number of protons, Z, but different number of neutrons, A minus Z, in their nucleus. Since they have the same number of electrons outside the nucleus, so their chemical properties are also same. In nature, different isotopes of an element occur in different proportion. In most of the cases, the relative abundance of one isotope is very high as compared to the others. Examples. 1. Hydrogen has 3 isotopes, namely protium H11 or ordinary hydrogen, which is most abundant, deuterium H21 or heavy hydrogen, and tritium H31. Each isotope in its nucleus has one proton, Z is equal to 1, but protium H11 has no neutron, deuterium H21 has 1 neutron, and tritium H31 has 2 neutrons. There is 1 electron outside the nucleus in the atom of each isotope. The table below gives the number of protons and neutrons in the nucleus of isotopes of hydrogen. Parameters: protium H11, deuterium H21, tritium H31. Values of Z and A for protium: Z is equal to 1, A is equal to 1. Number of protons: 1. Number of neutrons: 0. Values of Z and A for deuterium: Z is equal to 1, A is equal to 2. Number of protons: 1. Number of neutrons: 1. Values of Z and A for tritium: Z is equal to 1, A is equal to 3. Number of protons: 1. Number of neutrons: 2. Note: 1. Tin or Sn has the largest number of isotopes, that is 10. 2. The isotopes are of 2 kinds. A. Stable isotopes, which have the number of neutrons nearly equal to the number of protons in their nucleus. And B. Unstable or radioactive isotopes, which have number of neutrons much more than the number of protons in their nucleus. They undergo radioactive decay and are of great medical and industrial use. Example: in uranium 235-92, and uranium-238-92. Each isotope has 92 protons inside the nucleus, but uranium-235-92 has 143 neutrons, while uranium-238-92 has 146 neutrons inside the nucleus. In both isotopes, the number of neutrons is more than the number of protons, so both are the radioisotopes. Similarly, C14-6 is a radioisotope out of the three isotopes C12-6, C13-6, and C14-6 of carbon. Isobars. The atoms of different elements which have the same mass number A but different atomic number Z are called isobars. The atoms of isobars have the same number of nucleons A in their nucleus but different number of protons Z and different number of neutrons A minus Z. The number of electrons outside the nucleus is always equal to the number of protons, so isobars have different number of electrons. Examples: 1. Na2311 and Mg2312 are isobars. Na2311 contains 11 protons and 12 neutrons inside its nucleus and 11 electrons outside the nucleus, while Mg2312 contains 12 protons and 11 neutrons inside its nucleus and 12 electrons outside the nucleus. The total number of protons and neutrons is 23 in each. Examples: isobars. The atoms of different elements which have the same mass number A but different atomic number Z are called isobars. The atoms of isobars have the same number of nucleons A in their nucleus but different number of protons Z and different number of neutrons A minus Z. The number of electrons outside the nucleus is always equal to the number of protons, so isobars have different number of electrons. Examples: 1. Na2311 and Mg2312 are isobars. Na2311 contains 11 protons and 12 neutrons inside its nucleus and 11 electrons outside the nucleus, while Mg2312 contains 12 protons and 11 neutrons inside its nucleus and 12 electrons outside the nucleus. The total number of protons and neutrons is 23 in each. Protons. The atoms having different number of protons but same number of neutrons, that is, different Z and A but same A minus Z, are called isotones. They have different number of electrons. Examples: 1. Na2311 and Mg2412 are the isotones. Each nucleus has 12 neutrons. Na2311 nucleus has 11 protons, while Mg2412 nucleus has 12 protons. 2. K3919 and Ar4020 are the isotones, each having 20 neutrons in its nucleus. Radioactivity. Henry Becquerel discovered the phenomenon of radioactivity in 1896. Once in a dark room, he left a uranium salt placed on a photographic plate wrapped in a black paper. After some days, he was surprised to find that the photographic plate had been affected. Later on, the same observation was made with the other salts of uranium. From these observations, he concluded that uranium and its salts by themselves emit some kind of radiation which can pass through the cover that is black paper, glass or wood, etc., of the photographic plate and affect it. These radiations were called the Becquerel rays. On further investigation, these radiations were found to be of three types. 1. Positively charged, 2. Negatively charged, and 3. Uncharged, which were then named as alpha, beta, and gamma radiations, respectively. The substances which emit these radiations were called the radioactive substances. Radioactivity. The substances which disintegrate or decay by the spontaneous emission of radiations are called the radioactive substances. Example, uranium, radium, polonium, thorium, actinium, etc. Thus, the isotopes of nearly all the elements of atomic number higher than 82, that is after lead in the periodic table, are radioactive because in their nucleus, the number of neutrons is much more than the number of protons. These are called the natural radioactive substances. Activity is a nuclear phenomenon. Any physical change, such as change in pressure and temperature, or chemical change, such as excessive heating, freezing, action of strong electric and magnetic fields, chemical treatment, oxidation, etc., does not change the nature of radiation emitted by the substance and its rate of decay. This clearly shows that the phenomenon of radioactivity cannot be due to the orbital electrons, which could easily be affected by such changes. The radioactivity should therefore be the property of the nucleus. Thus, radioactivity is a nuclear phenomenon. It is the process of spontaneous emission of alpha or beta or gamma radiations from the nucleus of atoms during their decay. From a radioactive substance containing a very large number of atoms, there is no way to know or predict when or which nucleus of the atom will decay at any moment. Hence, the radioactive decay is a random phenomenon. That is, there is no law by which the disintegration of an individual nucleus can be known or predicted. Radioactivity as emission of alpha, beta, and gamma radiations. In 1903, Rutherford experimentally studied the nature of radiations emitted by the radioactive substances. He found that on subjecting the radiations given by a radioactive substance to a magnetic field in a direction perpendicular to their path, they separated out into three distinct constituents, as shown in figure, in which magnetic field is normal to the plane of paper inwards. Those which turn to the left, here the direction of deflection in a magnetic field is given by Fleming's left-hand rule, must be positively charged and are called the alpha particles, whose symbol is. Those which turn to the right must be negatively charged and are called the beta particles, symbol. The beta particles are deviated more than the alpha particles. Those which pass undeviated must be the uncharged or neutral and are called the gamma radiations, symbol. Gamma radiations are the electromagnetic waves similar to light waves and are therefore not affected by the magnetic field. Radioactivity as emission. Similarly, if the radiations given out by a radioactive substance are subjected to an electric field in a direction perpendicular to their path, they again separate out into the three constituents as shown in figure. Those which turn towards the negative plate are the positively charged alpha particles. Those which turn towards the positive plate are the negatively charged beta particles. Those which pass undeviated are the uncharged Gamma radiations. The beta particles are deviated more than the alpha particles. Properties of alpha particles. Some properties of alpha particles are given below. 1. An alpha particle consists of 2 protons and 2 neutrons. It is same as a doubly ionized helium atom, that is, a helium nucleus containing 2 protons and 2 neutrons. A helium atom which has lost its both the orbital electrons is called a doubly ionized helium atom. 2. The mass of an alpha particle is roughly 4 times the mass of a proton, means 4 mp. That is 6.68 into 10 raised to minus 27 kg, and its charge is twice the charge of a proton, that is plus 3.2 into 10 raised to minus 19 coulomb, or plus 2e. Thus, its specific charge, that is Q upon M value, is 4.79 into 10 raised to 7 coulomb per kg. 3. The speed of alpha particles is of the order of 10 raised to 7 meter per second. It is different for alpha particles emitted from the different radioactive substances. Further, all the alpha particles emitted from the nucleus of the same radioactive substance do not have the same energy or speed, but they have energy distributed in a small range. 4. An alpha particle strongly ionizes. An energetic particle, when suffers collision with the atom of a gas, it knocks out the electron from the atom, which now becomes a positive ion. This process is called ionization. The case of alpha particles. 5. An alpha particle rapidly dissipates its energy as it moves through a medium, and therefore its penetrating power is quite small. It can penetrate only through 3 to 8 centimeter in air. It can easily be stopped by a thin card sheet or a thick paper. Its penetrating power is roughly 1 by 100 times that of a beta particle and 1 by 1 lakh times that of gamma radiation. 6. Alpha particles are positively charged, so they are deflected by the electric and magnetic fields. The deflection of alpha particle is less as compared to that of beta particle because alpha particle is of more mass than the beta particle. 7. Alpha particle affect a photographic plate. 8. Alpha particles cause fluorescence on striking a fluorescent material. 9. Alpha particles have large kinetic energy and momentum with them. They are used to bombard the nucleus of an atom of one element to convert it into another element, that is, for transmutation. 10. Alpha particles destroy the living cells and also cause biological damage. 11th, alpha particles get scattered while passing through the thin mica or gold foils. Properties of beta particles. Some properties of beta particles are given below. 1. Beta particles are the fast-moving electrons emitted from the nucleus. Inside the nucleus, the change of a neutron into a proton causes the emission of beta particles. N01 gives proton 1, 1 plus electron minus 1, 0. The beta particles do not reside inside the nucleus of atom in the form of electrons of an atom. It is represented as beta minus 1, 0 or E minus 1, 0. 2. The rest mass of a beta particle is 9.1 into 10 raised to minus 31 kg, which equals Me, and its charge is minus 1.6 into 10 raised to minus 19 coulomb or minus E. Thus, the specific charge or Q upon M value of beta particle is 1.76 into 10 raised to 11 coulomb per kg. 3. Although both the beta particles and cathode rays are the fast-moving electrons, but they differ in their origin. Beta particles are given out from the nucleus of the atom, while cathode rays are given out from its orbital electrons. 4. The speed of beta particles is of the order of 10 raised to 8 meter per second, but always less than 3 into 10 raised to 8 meter per second. Different beta particles emitted from the same radioactive substance have different speeds. Beta particles emitted from a radioactive substance have energy distributed in a range from 0 to a certain maximum value. 5. Beta particles ionize the gas through which they pass. The ionizing power of beta particles is roughly 1 by 100th times that of the alpha particles, but nearly 100 times that of the gamma radiation. Properties of beta particles. 6. The penetrating power of beta particles is more than that of alpha particles, but less than that of gamma particles. They can travel through nearly 5 meters in air and pass through thin card sheet and even through thin aluminium foil, but a 5 millimeter thick aluminium sheet can stop the beta particles. 7. Beta particles are negatively charged, so they get deflected by the electric and magnetic fields. The deflection of a beta particle is in a direction opposite to that of an alpha particle, since the charge on beta particle is negative, while the charge on alpha particle is positive. The deflection of beta particle is more than that of the alpha particle, since a beta particle is much lighter than an alpha particle. 8. Beta particle affect a photographic plate. 9. Beta particles cause fluorescence on striking a fluorescent material. 10. Beta particles produce X-rays when they are stopped by the metals, such as tungsten, of high atomic number and high melting point. 11. Beta particles cause more biological damage than the alpha particles, as they can easily pass through the skin of our body. Properties of gamma radiations. Some properties of gamma radiations are given below. 1. Gamma radiations are the electromagnetic waves like X-rays and light, but they differ from X-rays and light in wavelength. The wavelength of gamma radiations is of the order of 10 raised to minus 4 nanometer or 10 raised to minus 13 meter, whereas the wavelength of X-rays is in the range of 10 raised to minus 2 nanometer to 10 nanometer, and that of light is in range of 400 nanometer to 800 nanometer. 2. The speed of gamma radiations is same as the speed of light, that is 3 into 10 raised to 8 meter per second in vacuum or air. 3. The ionizing power of gamma radiations is very low. It is 1 by 100 times that of alpha particles and 1 by 10,000th times that of beta particles. 4. The penetrating power of gamma radiations is high. It is about 10,000th times that of alpha particles and 100 times that of beta particles. They can travel through 500 meter in air and pass through 30 centimeter thick sheet of iron. A thick sheet of lead is required to stop them. Properties of gamma radiations. 5. Like X-rays and light, gamma radiations are not deflected by the electric and magnetic fields since they are not the charged particles. 6. Gamma radiations affect a photographic plate. 7. Gamma radiations cause fluorescence when they strike a fluorescent material. 8. Gamma radiations are also diffracted by crystals like X-rays. 9. Although X-rays and gamma radiations are similar in properties, but their origin is quite different. X-rays are emitted when there is transition of electrons in the inner orbits of an atom, whereas gamma radiations are given out from the nucleus. 10. Gamma radiations can easily pass through the human body, therefore they cause immense biological damage. 11. Gamma radiations are very useful in the treatment of cancer. Out of the three radiations, alpha, beta and gamma, the gamma radiations are more energetic and therefore they have a smaller rate of collisions with the atoms or molecules of the medium through which they pass. Thus they have least ionizing power but maximum penetrating power. On the other hand, alpha particles are least energetic and therefore they suffer more collisions. Thus they have maximum ionizing power but least penetrating power. Their energy is soon dissipated. Between the properties of alpha, beta and gamma radiations. First property, nature. Alpha particles are stream of positively charged particles, that is helium nucleus. Beta particles are stream of negatively charged particles, that is energetic electrons. And gamma radiation are highly energetic electromagnetic radiations. 2. Speed of alpha particle, nearly 10 raised to 7 meter per second. Beta particle, about 90% of the speed of light, or 2.7 into 10 raised to 8 meter per second. Gamma radiation, 3 into 10 raised to 8 meter per second in vacuum. 3. Rest mass of alpha particle, 4 times the mass of proton, that is 6.68 into 10 raised to minus 27 kg. Rest mass of beta particle is equal to the mass of electron, that is 9.1 into 10 raised to minus 31 kg. Gamma radiation has no mass, rest mass is 0. 4. Charge. Alpha particle has positive charge, 2 times that of a proton, is equal to plus 3.2 into 10 raised to minus 19 coulomb, or plus 2e. Beta particle has negative charge, is equal to minus 1.6 into 10 raised to minus 19 coulomb, or minus e. Gamma radiation has no charge. 5. Specific charge Q upon m. Specific charge of alpha particle is 4.79 into 10 raised to 7 coulomb per kg. Beta particle is 1.76 into 10 raised to minus 11 coulomb per kg. 6. Wavelength of gamma radiation is 10 raised to minus 14 nanometer or 10 raised to minus 13 meter. 7. Effect of electric and magnetic fields. Alpha particles are less deflected. Beta particles more deflected than alpha particles, but in a direction opposite to those of alpha particles. Gamma radiation are unaffected. 8. Ionizing power of alpha particle is maximum 10,000 times of gamma. Ionizing power of beta particle is less than alpha particle, 100 times of gamma. And ionizing power of gamma radiation is minimum. 9. Penetrating power range in centimeters. Alpha particle is small, 3 to 8 centimeters in air. Beta particle is large, up to few meters in air. And of gamma radiation is very large, up to a few hundred meters in air. 10. Stopping substance. Alpha particles are stopped by thin paper, human skin. Beta particles by about 1 millimeter thick lead or about 5 millimeter thick aluminium. Gamma radiations by about 30 centimeter thick iron or few meter thick concrete. 11. Biological damage. Alpha particles cause less damage, beta particles more damage, and gamma radiation immense damage. Changes within the nucleus in alpha, beta, and gamma emission. We have read that the radioactive substances are not stable. The nucleus undergoes spontaneous decay by the self-emission of either alpha, beta, or gamma radiation to form a more stable nucleus. The emission of alpha, beta, and gamma radiation is a nuclear change. In the emission of alpha and beta radiation, there is a change in the number of protons and neutrons inside the nucleus, while in the emission of gamma radiation, there is only a change in the energy of the nucleus and no change in the number of protons and neutrons inside the nucleus. 1. Alpha emission. If an unstable nucleus contains much more neutrons than the number of protons, it may emit a particle containing 2 protons and 2 neutrons tightly bound together, known as alpha particle. A stream of alpha particles is called alpha rays. If the nucleus X of a radioactive element of mass number A and atomic number Z emits an alpha particle, the daughter nucleus Y of a new element is formed, which has mass number equal to A-4 and atomic number equal to Z-2. Thus, due to emission of an alpha particle, atomic number Z decreases by 2 units and mass number A decreases by 4 units. This change can be expressed in the form of a reaction as follows. XAZ, the parent nucleus, gives YA-4 Z-2 daughter nucleus plus He42 alpha particle. Thus, the resulting nucleus has 2 protons and 2 neutrons, total 4 nucleons, less than the original or parent nucleus. Example, when a radioactive uranium nucleus U-238-92 emits an alpha particle, a new nucleus, thorium TH-234-90, is formed and the change is represented as follows. U-234-90 having 92 protons and 146 neutrons gives TH-234-90 having 90 protons and 144 neutrons plus He42 having 2 protons and 2 neutrons. Beta emission. When an unstable nucleus contains neutrons more than the protons, a neutron may change into a proton by emitting an electron for charge conservation. The electron given out from the nucleus at a high speed is called a beta particle. The change can be represented by the following equation. N10 neutron gives P11 proton plus E0-1 beta particle. A stream of beta particles is called beta rays. Note, later on, to keep the number of particles either odd or even on both sides, another particle called antineutrino, nu bar, was also assumed to be emitted along with the beta particle. This particle is uncharged and its rest mass is 0. Then the complete transformation equation becomes N10 gives P11 plus E0-1 plus nu bar. In emitting a beta particle, the number of nucleons in the nucleus, that is, sum of protons and neutrons, remains same, but the number of neutrons is decreased by 1 and the number of protons is increased by 1. In other words, by the emission of a beta particle, the mass number A does not change, but the atomic number Z is increased by 1. It changes into a new nucleus of element with properties similar to those of an element one place higher in the periodic table. The daughter product is thus an isobar having same mass number but different atomic number of the parent atom. If a radioactive nucleus P with mass number A and atomic number Z emits a beta particle to form a daughter nucleus Q with mass number A and atomic number Z plus 1, the change can be represented as follows. PAZ, parent nucleus, gives QAZ plus 1, daughter nucleus, plus E0 minus 1, beta particle. Example, a radioactive carbon nucleus C14-6 having 14 nucleons, 6 protons and 8 neutrons, emits a beta particle and changes to a new nucleus nitrogen N14-7 having 14 nucleons, 7 protons and 7 neutrons. The change is represented as follows. C14-6 gives N14-7 plus E0 minus 1. Gamma emission. In many cases, an alpha or beta emission is found to be followed by the gamma emission. It occurs when the daughter or the parent nucleus is in a state of excitation, that is, it has an excess of energy. This extra energy is released in the form of electromagnetic radiation, known as gamma radiation or gamma ray photon. The gamma ray takes no mass and no electric charge from the nucleus, that is, no neutrons or protons are lost. Hence, the nucleus does not decay into a different nucleus, that is, there is no change in the mass number A and atomic number Z of the nucleus in gamma emission. The gamma emission is represented as follows. XAZ, excited parent nucleus, gives XAZ, daughter nucleus, plus gamma radiation. Here the star indicates the excited state of the nucleus. Thus in gamma emission, the excited nucleus comes to its ground state. The table below shows the effect on atomic number Z and mass number A due to emission of alpha, beta, and gamma radiations. First, the quantity of Z decreases by 2 due to alpha emission, increases by 1 due to beta emission, and shows no change due to gamma emission. Second, the quantity of A decreases by 4 due to alpha emission, shows no change due to beta or gamma emission. Sources of radioactivity, radioisotopes. The isotopes of some elements with atomic number Z less than 82 are also found to be radioactive. They are called the radioisotopes. The nucleus of an atom becomes radioactive when number of neutrons in the nucleus exceeds the number of protons inside it. For example, cobalt, CO6027, Z is equal to 27, A is equal to 60. Carbon, C146, Z is equal to 6, A is equal to 14. Potassium, K4019, Z is equal to 19, A is equal to 40. Phosphorus, P3215, Z is equal to 15, A is equal to 32, etc. are the radioisotopes. The radioisotopes are also prepared artificially by the nuclear transmutation. They find their vital use in 1. Medical, 2. Scientific, and 3. Industrial fields. Medical use. First, many diseases such as leukemia, cancer, etc. are cured by the radiotherapy. Gamma radiations obtained from cobalt-60, CO-6027 are used to treat cancer by killing the cells in the malignant tumor of the patient. For radiotherapy, radiations must be able to penetrate the human skin. Second, the salts of weak radioactive isotopes such as radiosodium chloride, radioiron, radioiodine are used for diagnosis. Such radioisotopes are called the tracers. These tracers are used to detect the suspected brain tumors and blood clots before they become dangerous. The tracers are also used to study the natural process in the human body. For example, radiosodium chloride is injected with common sodium chloride in the human body, and the radioactivity of the blood at different parts of the body is tested to study the blood circulation. The process is called radiocardiology. Third, gamma rays emitted by the radioisotopes are used to sterilize bandages, dressings, syringes, and other equipments to make them free of germs. This method is quicker, more reliable, and cheaper than the process of sterilization by heat. 2. Scientific use. First, alpha particles emitted from the radioisotopes are used as projectiles for nuclear reactions. The scattering of alpha particles from the nucleus helps us in estimating the size of the nucleus and in understanding the nature of nuclear forces. Second, the radioactive tracers are used in agriculture science to study the growth of plants by using a particular chemical manure. Example, to know how readily a plant takes in phosphate and to which part of the plant the phosphate goes. Third, the age of excavated material of archaeological importance, rocks, and hence of buried plants, is estimated by the study of rate of decay of carbon-14, C14-6, in the remains of dead plants. This process is called carbon dating. 3. Industrial use. First, radioisotopes such as U-235-92 are used as fuel for the atomic energy reactors. Second, radioisotopes are used by engineers in factories to avoid the accumulation of charge on the moving parts of machines due to friction. The radiation emitted by the isotope ionize the air. The ions so produced take away with them the charge accumulated on the moving parts. Third, the ionizing effect of radiations from the radioisotopes is used in making certain luminescent signs. Fourth, knowing the penetrating power of the beta radiations emitted from the radioisotopes, they are used to control the thickness of paper, plastic, and metal sheets during their manufacture. Sources of harmful radiations. The main sources of harmful radiations are 1. Radioactive fallout from the nuclear power plants, 2. Nuclear waste, and 3. Other sources such as cosmic radiation and X-rays. 1. Radioactive fallout from the nuclear power plants. The nuclear power plants are now a major source of electricity in the world. If somehow there is an accident in the reactor of a power plant, a large amount of radioactive material and radiations will escape out into the atmosphere. This will not only affect the population around the plant, but will also affect the life at far-off places where they will reach due to air currents. 3 such accidents have already occurred. First, in USA on 28 March 1979. Second, in Ukraine in USSR on 26 April 1986. and third in Japan on 11 March 2011. These accidents caused damage to the reactor buildings and injuries to the persons working in the plants as well as to the persons in their vicinity. Nuclear waste. The fuel rods used in the nuclear power reactors are rejected when their activity decreases below a certain level. They then become a nuclear waste. These rods are still quite radioactive and are the source of harmful radiations. Therefore, they should not be dumped in open garbage. They can contaminate water and soil and affect the human and living organisms. 3. Other sources such as cosmic radiation and X-ray. The cosmic radiations from the sun enter the Earth's atmosphere from the outer space. They contain a large number of high-energy particles, out of which, although the charged particles are deviated by the Earth's magnetic field, but a substantial amount of uncharged radiations, such as gamma rays and X-rays, etc., reach the Earth's atmosphere. Some of these radiations are harmful for the human beings. Apart from this, the high-energy particle accelerators also produce the harmful X-rays. Harmful effects of radiation. The radiations produced in nuclear reaction includes alpha radiations, beta radiations, neutrons, gamma radiations, and X-rays. They interact with the living tissues within 10 raised to minus 14 seconds and cause biological damage. The biological effects of nuclear radiations are of 3 types. 1. Short-term recoverable effects like diarrhea, sore throat, loss of hair, nausea, etc. 2. Long-term irrecoverable effects like leukemia and cancer. And 3. Genetic effects. The first and second effects are limited to the individuals who are actually exposed to the radiations, while the third effect appears in the later generations of the person exposed to the radiation. The genes in his cell get modified or mutated. Harmful effects of radiation. The exposure to radiations can be acute if there is an accidental burst of radiations from an unshielded source. Similarly, it is chronic in case of persons working in atomic energy establishments when they get exposed to such radiations. The exposure of pregnant women to X-rays for a long time may affect the child in the womb. It increases the risk of cancer by 40%, of tumor and nervous system by 50%, and of leukemia by 70%. The exposure of upper part of the body to X-rays may damage the thyroid glands and can cause cancer. The exposure to gamma rays destroys the cells of the body and affects the blood cells, gastrointestinal tract, reproductive and hair cells. It can harm the DNA and RNA of the living cells also. The uncharged neutrons also cause biological damage. Safety precautions while using nuclear energy. We have read that nowadays electricity is also generated by the use of nuclear energy obtained from the nuclear power plants. In a nuclear power plant, a radioactive source such as uranium-235 or plutonium-239 is used, and the controlled chain fission reaction is carried out. In this process, the following aspects require special care. 1. Establishment of nuclear power plants. 2. Handling of radioactive materials. And 3. Safe disposal of nuclear waste. 1. Safety measures while establishing a nuclear power plant. While establishing a nuclear power plant to generate electricity, following precautions must be taken. First, ensure that the people working in it are not exposed to nuclear radiations, and in case of any accidents, there is a minimum spread of radiations. Second, The nuclear reactor of the power plant must be shielded with lead and steel walls so as to stop radiations from escaping out to the environment during its normal operation. Third, the nuclear reactor must be housed in an airtight building of strong concrete structure which can withstand the earthquakes, fires, and explosions. Fourth, there must be a backup of cooling system for the reactor core so that in case of failure of one system, the other cooling system could take its place and the core is saved from overheating and melting. 2. Safety measures while handling radioactive materials. People working with radioactive materials are required to follow strictly the safety measures given below. First, they should put on special lead-lined aprons and lead gloves. Second, they should handle the radioactive materials with long lead tongs. Third, the safety limit for each type of radiation is known. Therefore, care must be taken to ensure that no one is exposed beyond the safety limit in any case. For this, special film badges are used, which are tested from time to time to know the amount of radiations to which a particular person has been exposed. Fourth, the radioactive substance must be kept in a thick lead container with a very narrow opening so as to stop radiations coming out from other directions such that it absorbs the radiations which strike on its walls from inside. Alpha particles can easily be stopped by a thin metal sheet, but for beta particles, we need a thick metal sheet. Safety measures in safe disposal of nuclear waste. The radioactive material after its use is known as nuclear waste. The nuclear waste obtained from laboratories, hospitals, scientific establishments, or power plants must be first kept in thick casks and then they must be buried in the specially constructed deep underground stores. These stores must be made quite far from the populated areas. The casks can also be buried in useless mines, and these mines must be sealed after storing the casks. Background radiations. The background radiations are the radioactive radiations such as alpha, beta, and gamma to which we all are exposed even in the absence of an actual radioactive source. Sources. There are two sources of background radiation. One, the internal source. The radioactive substances such as potassium K40 and carbon C14 and radium present inside our body. K40 and C14 are present in our entire body and they affect all parts equally, while radium is largely found in bones and so it affects only the bones and the reproductive organs. And two, external source. Cosmic rays, naturally occurring radioactive elements such as radon 222 and solar radiations. It is not possible for us to keep ourselves away from the background radiation, but the total background radiations from both the internal and external sources do not exceed the maximum permissible dose for human safety, so we need not worry. Maximum permissible dose. The effect of different radiations on human tissue is measured in unit sieverts SV dose. In one exposure of X-rays for chest, the patient receives 0.2 millisieverts dose of radiation. Energy. In a nuclear change due to a radioactive phenomenon such as decay, fission, or fusion, the total sum of masses of product, nuclei, is always less than the total sum of the masses of reactant nuclei. Thus, there is a loss in mass. In 1905, on the basis of theory of relativity, Einstein suggested that mass and energy are interchangeable. Due to loss in mass, m, the energy released is E, where E is equal to delta m c square. Let this be equation 2. Here, delta m is the loss in mass in kg. C is the speed of light, which is equal to 3 into 10 raised to 8 meter per second. And E is the energy in joule, J. The energy so obtained is called the nuclear energy. T equivalent to mass 1 kg. When 1 kg mass is lost, the amount of energy released is E is equal to delta m c square is equal to 1 into 3 into 10 raised to 8 whole square is equal to 9 into 10 raised to 16 joule. Since 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joule, therefore, E is equal to 9 into 10 raised to 16 upon 3.6 into 10 raised to 6 kilowatt hour is equal to 2.5 into 10 raised to 10 kilowatt hour. Thus, 1 kg mass is equivalent to 9 into 10 raised to 16 joule or 2.5 into 10 raised to 10 kilowatt hour of energy. Energy equivalent to mass 1 AMU. In class 9th, we have read that the mass of atomic particles is expressed in atomic mass unit, AMU, or unified unit, U, where 1 AMU is equal to 1 upon 12 into mass of 1 atom of carbon-12, or 1 AMU is equal to 1 upon 12 into 12 into 10 raised to minus 3 kg upon 6.02 into 10 raised to 26 per kg mole is equal to 1.66 into 10 raised to minus 27 kg. Due to loss in mass, delta m is equal to 1 AMU. The energy released is E is equal to 1.66 into 10 raised to minus 27 into 3 into 10 raised to 8 whole square joule is equal to 1.49 into 10 raised to minus 10 joule. But 1 mega electron volt is equal to 1.6 into 10 raised to minus 13 joule. Therefore, E is equal to 1.49 into 10 raised to minus 10 upon 1.6 into 10 raised to minus 13 mega electron volt is equal to 931 mega electron volt, or 1 AMU is equal to 931 mega electron volt. Let this be equation 3. Thus, 1 AMU of mass is equivalent to 931 mega electron volt of energy. Note: the mass of an electron, proton, and neutron in terms of kg, AMU, and mega electron volt are as follows. Mass of electron is equal to 9.1091 into 10 raised to minus 31 kg is equal to 0.00055 AMU is equal to 0.511 mega electron volt. Mass of proton is equal to 1.6725 into 10 raised to minus 27 kg is equal to 1.00727 AMU is equal to 938.3 mega electron volt. Mass of neutron is equal to 1.6748 into 10 raised to minus 27 kg is equal to 1.00865 AMU is equal to 939 mega electron volt. This can be summarized as below. Particle and their mass. 1. Electron 9.1 into 10 raised to minus 31 kg, 0.00055 AMU, 0.511 mega electron volt. 2. Proton 1.6725 into 10 raised to minus 27 kg, 1.00727 AMU, 938.3 mega electron volt. 3. Neutron 1.6748 into 10 raised to minus 27 kg, 1.00865 AMU, and 939 mega electron volt.